The topic of this video is wave equation. We will first look at the simple wave equation and the visualization of its solution. Then we will visit the standing waves with different number of nodes and see how the change in tension affects the solution. We will end this video by exploring traveling waves and standing waves. Here is the generalized form of 1D wave equation. Unlike the heat equation, there is a second derivative with respect to time. Also, two initial conditions are needed, one for u, which is the vertical displacement of the wave, and one for the derivative of u with respect to time. One specific solution to this problem is visualized on the figure. Solution at each t looks like a simple oscillation along the x-axis while the amplitude changes. This is called a standing wave. The equation on the bottom is one specific solution to the wave equation with the boundary conditions and initial conditions shown on the previous slide. Here, the parameter c is simply a square root of the tension over density, and the term n pi c over L is the circular frequency, which is the number of oscillations in 2 pi units of time. The figure on the left shows the solution with n equals 1, the first harmonic. We can see that the solution has 0 nodes. The figure at the middle shows the solution with n equals 2. This is called the second harmonic and has one node at the middle of the domain. Here, the second harmonic has twice as higher frequency compared to the first harmonic because the n term in the circular frequency doubled while the other terms stay the same. The figure on the right is the case with n equals 3, the third harmonic. It has two nodes and has an even higher frequency as expected. We can notice from these figures that the nth harmonic wave has n-1 nodes. What will happen if we vary the tension of the string? The left figure shows the first harmonic wave with tension equals 10, and the right figure shows the first harmonic wave with tension equals 100. The higher tension leads to larger C, leading to higher circular frequency. This explains why the right figure has much higher frequency compared to the left figure. This phenomenon is easily observed when we tune a string instrument, such as a violin or a guitar. Varying the tension of a string leads to different frequency of vibration, producing different pitch. We can also vary the pitch if we change the effective length L by clamping down the string. Now let's look at the traveling waves. In this figure, the red sine wave, U1, is traveling to the right, while the blue sine wave, U2, is traveling to the left. The pink wave is the average of the two traveling waves, and we can see that the marker on the wave does not travel to left nor right, but only moves up and down. By adding up the two waves traveling to the opposite direction, we have obtained a standing wave. Now, what will happen if we use waves other than the sine or cosine functions? The same phenomenon is observed for the rectangular waves and triangular waves as well, as shown on the figures. Each standing wave is composed of the two waves traveling in the opposite directions.